Hi everyone, today we're going to be talking about our project AutoTranscriber. Next slide, please. So the goal of our project is to automate music transcription for solo piano. And so that involves taking in an audio WAV file and outputting something called a MIDI file. And the MIDI file just stores information about music played by different instruments. And it's stored in such a way that computers can reconstruct it using different software into kind of like digital sheet music. In our case, it's represented as a 2D array. And the purpose of our project is to just make music more accessible for people. Next slide. And so we know that sometimes networks pick up on the wrong patterns, and that kind of happened in our case. Our network was able to converge, but it also converged on the wrong pattern, but we'll discuss that more in results. Next. In terms of pre-processing our data, we started off with a WAV file, and we went through a series of steps to generate something called a spectrogram. Next slide. And a spectrogram, very briefly, is just a NumPy array of 229 by 126. And we got those dimensions because we chose a 4-second long input, and it has normalized values across the training set. If we look at the diagram on the right, the x-axis represents the time frames, the y-axis represents the frequency, and the color scale represents how loud that frequency was played at that point in time, and is measured in decibels. Next. As I mentioned before, we output a MIDI file, and it's readable by music notation and editing software such as MuseScore, and it has components like pitch, duration, volume, and more. Next slide, please. Just very briefly, if we load that MIDI file into a MIDI editor, for example, number one, it shows what instrument is playing what. Number two, it has the time frame. And number three, it shows what sequence of notes and at what pitches those instruments are playing at each point in time. Next, Richard will talk a bit about data collection.
Yeah, so in terms of data collection, we used a publicly available data set from Google's Maestros, and it was a rather large data set. So from that, we took around 9,000 samples and performed a 95-5 split for test, train, and validation. We also had independently collected data, which was in the form of manually recorded piano samples. And we played those off of existing MIDI files for time efficiency's sake. The trade-off there was we needed to perfectly sync each note with when it showed up in our MIDI files. And obviously that had its difficulties and wasn't perfectly done. And we'll talk about how we address that later. Next slide, please. In terms of our model, we have our input, which goes through 3 convolution layers, each with its own max pool. Then it's passed through a fully connected layer into a GRU unit, and then back into another fully connected layer, and then we get our output. Most of these layers all utilize batch normalization as well as dropout. Next slide, please. In terms of optimizers used, we used RMS prop and a loss function of BCE log its loss. We couldn't get down with using Atom because our model was too large and the adaptive parameters taken in with Atom was too much for our GPU memory that we had. Next slide, please.
So I'll be talking about qualitative results now. So here's just 2 samples, one on the left, one on the right. Each graph is of MIDI note versus the frame. So as Kat mentioned earlier, the MIDI files can be represented as 2D arrays. And on top is the ground truth and bottom is the network predictions, which is also a 2D array. So I'll start at the left. This is taken from earlier in the training. And you can see that the network predictions, which are the little dark blue dots, they cluster around where the ground truth MIDI notes are. And later in training, we realized that the network prediction, or the network predicts all zeros. And this is because this actually reveals a problem with our labels, which is that it's too sparse. So there's too many zeros and not enough ones, which are the notes that are on. Next, please. So I'll talk about a couple of metrics for our quantitative results. The first one's element-wise accuracy here, and it just looks at the total number of elements that are the same between the prediction and label and divides that by the total number of elements. Next, please. So the second last metric that we'll look at is the variable window size. So this, for each column in our prediction, it looks at the corresponding column in the label and generates a window. Here it's a window size of 3. If the column in the prediction matches any of the columns in the label, then we count that as a match. Otherwise, it's not. And we just look at the total number of columns that are a match and divide that by the total number of columns to give us an accuracy. Next, please. Yep. So for the element-wise, this is a pretty intuitive way of measuring accuracy. And here we can see that the accuracy on the left, it increases with both training and validation over time. However, this just reflects what our model learned that we saw in the qualitative results, which is that it just predicts all zeros. Next, please. So the second quantitative results we'll talk about is the variable window size. So the intuition behind the variable window size metric is that, as Richard mentioned earlier, our audio samples do not necessarily sync up with our ground truth labels perfectly as we record them ourselves. So the window is meant to account for some time variance in that respect. So from left to right, we have window sizes of 1, 5, and 11. So that's varying the window size. And you can see that both the train and validation accuracies increase over time, but in the context that our model only predicts basically zeros, this just reflects how many perfectly silent columns there are between the prediction and the ground truth. Next, please. So a couple learnings. So intuitively, yes, our results make sense given the data set. So in particular, we saw that the labels, since they're so sparse in ones, which are the MIDI notes are on, they have too many zeros, resulting in our model just predicting all zeros. And some things we would do differently. So one thing would be adding more information about the music. So for example, note onsets, which is just the instant that each note is played. Several other models and architectures done by other people and companies use features such as these to improve their networks. That concludes our presentation, and thank you for listening.
Great. Oh, perfect timing. Thanks. It's really interesting. I have a couple. It's an interesting attempt. I get that it didn't work as well as you had hoped. I guess my big question is, you talked about changing your measure of accuracy. It's a topic of conversation today, actually. It's really the third group we're talking about that. And you changed it to, let's find that, to this metric, right? That was your accuracy metric. Did you change your loss function in any way related to this?
No,
no, we didn't. The loss function was like, we just had two separate accuracy metrics, but the loss we computed was the same for both of these.
Which was what? The element?
The BCE log its loss.
Which is more aligned with the element wise.
Yes.
Yeah.
Yeah, this is actually very similar, I think, to what the couple groups ago referred to as the dice function. And there's various methods of where dice is the actual loss function, and there's ways to make the minority class have more power. You basically pump it up in the loss function. You give it a higher weight, and so I don't know if Phil, you knew about that, or you had a chance to advise that. So if you have a moment or two, you might play around with the loss function to see if you can do that. That give higher emphasis to the non-zero elements in your that are being used to compute your loss function. Does that make sense? I'm not sure I'm being coherent.
Yeah. I was gonna say the same thing. If you go to your loss, can we take a look at the loss?
I don't know if it's here. Where is it?
It's slide 10.
Sorry, Phil, do you mean the loss function or the loss slides?
The loss function, yeah.
Okay.
Yeah, I guess I'm not familiar with, what this is actually computing. But as Jonathan said, cross entropy, for example, should penalize more. It should add more value to computing loss for the minority classes. So, for example, even if you have a sparse matrix, your model should learn the fact that it needs to predict a certain amount of ones.
Well, no, that's not built into BCE with logic's loss. It treats the ones it treats the wrong answers with a severe punishment, but there are not many wrong answers across the matrix. So you have to weight the one answers more heavily. You actually have to pull that out and think about computing that separately rather than using a prefabricated loss function here. You know what the BCE loss is because I've taught it to you. So you could still use that very harsh punishment against wrong answers, but separate out the positive ones from the negative ones and give those positive ones equal weight to the negative ones, rather than they're getting much less weight when you just treat them equally because there's so few of them. So you might, if this makes sense to you, and maybe Phil, you understand what I'm talking about. You guys can talk about this. You might just try and see if that helps a lot, because this is a common problem in other venues about very unbalanced. It's not classes. I guess they each.
It's class balance. Yeah.
Yeah. I guess it is classes. Yeah. So that, I think that's a really crucial thing. The most important thing to feed back to you. I liked your introduction, motivation, and it's kind of clear what you're working on. So it's worth. It's important to say that. Yeah. Did you have any other comments, Phil?
Yeah. So I was just wondering, how did you guys discover the really sparse predictions?
Oh, well, it was basically in slide 11, right? Like at first we thought we were like outputting our answers wrong, but then we essentially printed out for each 25 gradient steps. We just printed out the max value in each prediction, and we realized that like the max values were just dropping slowly to 0.
Yeah, that's really great. I think it shows the importance of actually visualizing the raw predictions and what your model is actually learning. So I think that's super valuable. Yeah.
Yeah, that's a really good point. That's the whole point of this part of the point of this qualitative section I've asked for. But it also means you have to think. You always have to be thinking about the problem itself and seeing where the answers are going. You did better than this, though, right? Because this says you got nowhere, but you did get somewhere, right? Some of these were non-zero. Is that correct?
Yeah, they weren't all 0, but this is after we run it through a decision function, which drops everything below 0.5 to 0 and everything above to 1. Yeah. And I think all of our answers were like below 0.05 or 6 by the time we were done.
So did you
so it all just ended up dropping to 0.
But you got non-zero answers ultimately, though, right?
Yes. Yeah.
How did you do that then?
That was before we fed it into our decision function.
Sorry, what was before you fed it into?
The non-zero value. So we got the 0 values after we got after we fed it through our decision function. So our raw prediction value.
So essentially, you're saying you changed your decision function to somehow. Is that right?
I believe we stopped after some number of batches. And that's how we got the diagram on the left in slide 11.
Slide 11. What about this? But what I'm asking is, how did you? Oh, so is the diagram on the left is the one that you based your decision, your final results on?
No. So that was the diagram on the left is just meant to illustrate like it obviously doesn't start off guessing zeros. I think this was taken.
Okay.
Like a quarter way into the training process. Yeah.
Okay. So what I'm trying to figure out is, how did you get any results at all? And I get that something happened with the decision. Maybe something happened with the decision function. But tell me what you did after this problem became apparent to actually get anything.
Can I try answering that, if you don't mind? Okay. Cool. Yeah. So I think you're asking like, why aren't the plots just all 0, right? For the accuracies.
I'm asking, what did you do to fix that? Yeah.
Yeah, so at the end of training, our network predicts all zeros based on our decision function. We don't change that. And so here for the quantitative results, the element-wise, basically we achieve high accuracy only because the ground truth labels themselves have so many zeros. And then similar for the
But what about
similar for this one. It's just much harder to match columns since this one looks at columns rather than elements. So this basically shows how many 0 columns there are common between our prediction and the ground truth label.
Okay. I get it now. Yeah, well, if you've got time, I'd really urge you to try to just push harder, to change your loss metric.
Yeah, for sure.
Yeah, or just like a very simple thing you can do is change the threshold of the decision function. If, or have this as a hyperparameter, right? Because if your threshold, is constantly everything's below or like hovers around 0.05 instead of 0.25, you can just change that to get a certain percentage of positives.
Yeah, but it's just from what they're saying, I would go with the other thing first. Just get a parameter that you sweep that says, I care about these ones more than I care about all those zeros. That's the place to start, because and then once you see more activity in the outputs, which hopefully you will see, correct activity, then maybe go for the loss function, but the decision function. Yeah.
Mm-hmm.
Okay. Cool. Okay, we better get going on to the next one. Thank you very much.
Thanks.
There's a lot to learn here for everyone, actually. This issue is one that does show up in certain kinds of problems.